so we can move on to the last notebook of today, which is on another common geographic analysis type called nearest neighbor analysis. So we will be trying to first, again, a bit conceptual, and then working with some real world data. And then we will be trying to figure out, which points are the closest to other points or objects. So again, we will be using Shapely objects to figure out or to conduct the nearest neighbor analysis. So let's start with the first code cell here that is already filled out. We load in from Shapely geometries, we load in point and multi-point, and from the Shapely operations, we import nearest points function. And then we create, for this first example, we create one origin point and then 3 destination points. And we will see which of the destination points is the nearest to the original point. So we run this cell to read in the different points. And then to be able to quickly find the closest destination point from the origin point, we will create a multi-point object from the destination points. So we get all the 3 destination points within one object. So to do that, we will create a multi-point and pass it a list of different points. So we pass it dest1, dest2, and dest3. And let's save that multi-point into a variable called destinations. All right, so we can print out destinations to see what it looks like. It's a multi-point here with the different coordinates for the 3 points that we started with. And we can check it out visually as well with destinations and see that we have 3 different points, but they're all within one multi-point object. So that is good. They are represented as one object. So then we can find the nearest destination point from the origin point using the nearest points function. So we start by typing nearest points function, and then we pass it the origin point and then the destinations that we want to look at. So we have our orig point and we have our destinations multi-point. Let's save that into a variable called nearest gems and run it. So, all right. So let's check out what that actually returns. We can check the type of nearest. That's nearest and run that again, just to make sure I don't make many typos. Nearest gems, and we can see it's a tuple object. So let's take a look at what's inside the tuple. We can print the nearest gems and see here we have a tuple with 2 Shapely point objects. So if we try to access each of those points to see them, we can do that by printing nearest gems and take only the first point in that list and see that it looks like this, and then take our second by copying that and changing to the last object. Okay, So what we can see here, the first first part of the tuple has a point, a shapely point that is the same as the orig point, the origin point that we created, and the second one, second part is also a shapely point with 0 and 1.45 as coordinates. So that was the destination 1, the first destination point. So the nearest points function returns a tuple of which of the points from each of the objects that we pass into it, which of the points from those two are the closest. So we could also have a list or a multi-point as origin and a multi-point as destinations, and it would find the point from the first that is closest to the point in the second. But here we only had one origin point, so that is the first part of the tuple, and then the nearest in the multi-point is in the second part of the tuple. Okay, I hope that was somewhat clear, as we will proceed to use it on real world data and not just these arbitrary values. So we will try to do some nearest neighbor analysis in Geopandas or with our Geopandas data frames that we create. So let's start again with importing Geopandas. And then we have our district data that we've used before and our addresses shapefile, geocoded addresses. So we define the file paths, we enable the KML driver, and then we read in the two data frames, data sets. All right, so then we can just take a look at the first geodata frame. See the head of that. See, we have our districts that we know from before, and also inspect our second geodata frame to see what's in there. And that's our geocoded addresses with shapely points. Yes, so as you remember in the last notebook, before doing spatial operations, it's a good idea to make sure that we are using the same CRS for the two different data sets. So we will now just make sure that they are the same coordinate reference system by projecting or reproject the two data frames into the same CRS. So we will take our first data frame and replace it with a data frame that is projected to the CRS EPSG code that is 3067 for our instance, and then we will do the same for the second geodata frame. So yes, when we are calculating distances, so which one is close, points that are closest to other points, we want to have our data in a projected CRS. So if we run this cell, then both our data frames are projected into the same coordinate reference systems. So then we can calculate the distances from that. Yes, and so now we want to, in our districts data frame, we want to create a centroid point for each of the districts that we can calculate the nearest neighbor to. So to do that, we create a column in our first data frame called centroid, and we will use as it's a Geopandas data frame, we can take df1.centroid, and that will calculate the centroid for the entire series or the entire data frame. So if we take df1.head and take a look at that now. We see that we have the same district polygons, but we have also calculated a centroid point for each of them. Okay, so far so good. So what we're going to do now is to, in the next cell, we have created a function that that goes over the that figures out the nearest address point and fetch some of the attributes that is related to that address point to the district table. So it looks at each row in the district table and then finds the nearest point based on the centroid or the geometry of the district, and then compare all the different addresses and finds which is the closest to the centroid point of each row. Okay, it might be a bit difficult to explain, but it will hopefully be a bit more understandable when we run it. So I'll just create this function into memory. So I can try to explain again what it does. It is a function that takes 4 different parameters. First, it takes a row of data, and then it takes another geodata frame. And then as input for point column, it defaults to geometry. And for the value column, it also defaults to geometry. So what it does, it takes from the other geodata frame that we pass into the function. It takes the geometry and it creates a union operation on those geometry objects, and then below it then does a nearest points analysis of the point in the row and all the other points from the other geodata frame. And then it takes from the other geodata frame, it locates the nearest geometry point, so the nearest neighbor in the other data frame, finds that and returns the values that we want to get out from the other data frame. Okay, let's try to look at how it works in practice. So let's start by creating or checking out how unary union works that we are using in the function. So let's call create a variable called unary union, and from our second data frame, which you remember was our addresses data set. So from our addresses, we do create a unary union, and let's print out that to see what that function actually does. So it creates a multi-point from all the different points in our addresses data frame. So a very long here. So if we try to do this, you can see it plots one object, but that contains all the 34 different addresses that we had in our data. Okay, I hope that made sense. So it basically just creates a multi-point in a quick way using unary union. Okay, so we have created that. And now let's try to apply our function that we created up here to the first data frame. Yes, which you remember is the district's data frame. So in the district's data frame, we will see apply this function here that finds the nearest neighbor in our addresses. So we take the first data frame and we apply a function. So the apply method from for the data frame takes a function first. So get nearest neighbor is the function that we want to apply. Nearest values is what we called it above here. And as all the different or all the other attributes or parameters that we pass the apply function is the necessary parameters for that function that we are running. So one easy way we can to make sure we get all that we need is to take the parameters from up here, from where we created the function, copy those, and then after a comma here, paste them in. So now we have here our first data frame. We apply one function, and then actually instead of the row here, we can take out that, because at the end of apply, it also takes a parameter of what axis of the data frame that we want to apply it to. So if we want to apply it to column-wise operations, then that's the 0 axis. But if we want to do it for all the rows, that's axis 1. So we need to pass it axis equals 1 in the end here. Yes, so let's just recap here. We have our function that we're running. We have our other geodata frame. We need to specify which geodata frame that is. That is the addresses, which we called df2. And then for point column in our first data frame, that is called here. If we just remember here, those points are in the centroid column. So for point column, we will pass centroid. And then we will start by, let's start without the value column, as it is, as we saw above here, it is default to geometry. So we will use geometry, so we don't need to pass it here. But so in order to run this apply function, but also keep the data output that we want, we will do that to a new column in our df1 data frame. So we will find the nearest location. We'll call our column that. And yeah, so in this new column, the results, it will be populated by the function that we apply to the data frame. Okay, let's try to run that and then see what our data now looks like. So if we inspect the head of our data, we can see that for each district, we have the geometry column. For the entire district, we have the centroid of each district, but we also have the nearest location from the addresses data frame. Okay, so that is good. It was able to find a point from the multi-point of all the addresses that is closest to each of the centroid points. What we could also do is, if we wanted to get more another value output from from the addresses data frame, we could, let's copy this line and paste it here. And then for our value column, value column, get the ID of each of those points, of the nearest location points. So we could do nearest location ID, for example, here. And if we run that cell, then and take a look at our first data frame in a new, how it looks now, it has a new column with the ID of the point that is closest to the centroid of that district. So, for example, you can see that point 1017 is closest to the centroid of two different districts in Espoo. So, as our addresses were public transport stations, it does make sense that at some districts the public transport station is located so that it serves two different districts equally. All right. Did that make sense? I feel that it was not the best explanation necessarily. And I see someone got the same ID for all rows, which sounds a bit, I'm not sure how that happened. So I can try to repeat how the function works. So the function takes one row as input, then it takes from that row, it selects the point geometry that we want to use. And then it takes from another geodata frame. So in our case, the addresses data frame, and creates a unary union for that geodata frame. So as we saw, if we run this cell again and plot the output from that, it creates a unary union, so a multi-point from all the different points. And then we do a nearest point analysis, nearest neighbor. So we have our 1 point from that row of our district's centroids. So if that is located here, then it looks at all the different points and figure out this is the point that is closest. And then in the value column, we take that point, locate it in the addresses data frame, and select the value column, which, if we change that to ID, takes the ID and returns that ID value. Yes, and then we added that as a new column to our first data frame. So yes. So I hope that made sense. The example the function might be a bit cumbersome way to explain it, but you will get in the exercises, you will get the opportunity to test it out in different ways, or for some other data that we will be using. Yes, so we can, as we are okay on time, I can just open the last two notebooks without running and explaining everything, because these are optional for you. So the spatial index notebook first describes and explains how a spatial index work in Python. So if you have in some GIS software, if you're working with bigger data sets, you might have gotten a warning or a pop-up saying, should we build like a spatial index for your data to make it the spatial queries run faster? And we can do the same thing in Python to build an index that makes the queries run faster, so that it doesn't look through all of the data at once, but figures out what the best indexing is to do that. So we can do that in Geopandas as well, and look at that. So yeah, so creating spatial indexes and how those work is useful in working with larger data sets. The data sets we are working with are usually relatively small, so it's not always needed. But if things are if your analysis is going slowly and it's because you're working on a large data set, then spatial indexes might be good to read up on and take a look at. So that is that notebook. And the last notebook is also on nearest neighbor analysis, but with larger data sets. So here is some other packages and modules for doing those kind of analysis is also introduced. So if you are using large data sets, then it might be necessary to create these spatial indexes and ball tree indexes. Yeah, but I won't go into the details about them, but they are more there as a motivation if you want to learn more about it, and if you in your final project want to work with large data sets. Then both spatial indexes and nearest neighbor analysis and spatial indexes in that sense might come in very handy and be almost necessary